Hello everyone, today we're going to do another example question on calculating regarding towards equilibrium constant. Okay, so for this question, so you will know the initial concentration. So again, we're going to use the brackets to represent concentration and initial, and you will also know the equilibrium constant, so that will be Kc, and then you're looking for the equilibrium concentration, so we will use the brackets and EQ to represent it. And then now let's see for the example question we have right over here. So you will know the Kc value, and you will know the initial concentration, and you're looking for the equilibrium concentration. So exactly what we just said. So for this type of question, again, you need to use as table. So you're gonna need to use as table. So let's start from expressing our Kc first. That's always helpful. So your Kc equilibrium constant is equals to products raised to its stoichiometric coefficients to that power. So it's gonna be 2 over reactants. So this is the equilibrium constant expression, and we know this value equals to 0.36. So that's what we know, and then again, all these concentrations will be at equilibrium. And we don't know, we don't know neither of this. So we don't know these two concentrations, so we need to figure out, and then we'll be able to figure out the answer for the question. And then the given information is that the initial concentration of NO2 initial equals to 0.1. And then we know we need as table to help us to find out what's the expressions for the concentrations at equilibrium. I always encourage you to have your equation with you. So I'm gonna put the balance equation on top of my S table, so I will remember what's the ratio, what's the coefficients. So in this case, the coefficients is 1:2 ratio. So 1:2 ratio. Now let's draw our S table. So it's ICE. C is change. Initial, equilibrium, the whole table based on molarity. So that will be N2O4 and NO2. And initially we know the concentration for NO2, which is going to be 0.1. And then for the N2O2 and N2O4 initial concentration is going to be 0. It's implied because initially you only have the NO2. So like we said, the next step you will be expressing Q and then compare with K. So let's do that. So the Q value, so the QC value will be the same expression, however, instead of the concentration at equilibrium, it will be the concentration at this moment, whatever moment you're trying to calculate. At this moment will be initial. We're trying to calculate the Q and determine which direction will proceed. So in this case, NO2 will be 0.1 squared, initial concentration 0. So when you do this, you know mathematically after the calculation, this value is going to be infinite. So it's going to be infinite. And then now we're going to compare Q and K. So we're going to do that. So QC will have infinite. Of course, this is going to be bigger than Kc. Kc value is 0.36. And then this tells us the direction going to go to the left, go to the reverse direction. This helps us to determine the signs over here for the change. So for the change, so since the direction goes to left, so the change will be negative for the product and positive for the reactant. Think about it. Make sure it makes sense to you. So because you only have products in your container, where the reaction has to go to the left to make more of reactants. Okay, so in this case, there's gonna be negative 2x. Okay, and this will be positive x. The ratio comes from right over here, right? Like 2 is coming over here. Okay, that 1 is over here. Because just 1 we just don't write it out. Okay, so that's all we have. And then again, that QC and KC comparison helps us to figure out this role. Okay, the change. Okay, so now we have that, and things get really easier. Okay, so now we just need to express the equilibrium concentration. Remember, we're looking for the final, and then now equals to initial plus change. Okay, so it's gonna be x. Over here will be 0.1 minus 2x. Okay, so that'll be the concentrations at equilibrium. Okay, so now we can put this back into our expression earlier over here. Okay, and then we'll just have one variable as x and then solving for x. Okay, so that's not bad. Okay, so now let's do that. Okay, so I'm gonna put Kc equals 2. So now it's going to be 0.1 minus 2x squared over x equals to 0.36. Okay, so now I have this, and then that's from here, and we just need to solve for x. Okay, so the top part, when you have the squared, you will do this. So it will be 0.1 squared minus 2 times 0.1 times 2x plus 2x squared equals to 0.36x. I just cross multiply x to the other side. Okay, now you just simplify this expression, so it's going to be 0.01 minus 0.4 x plus 4x squared equals to 0.36x. I'm going to put x to the left side, and then I'm going to organize into this order. So we'll have negative 0.76x plus 0.01 equals to 0. Okay, at this point, you go, this seems like not easy to solve this. Yes, we can use quadratic equation. Okay, so the equation will be following this format: ax squared plus bx plus c equals to 0. The quadratic equation will be x equals to 2a negative b plus minus b squared minus 4ac. Okay, in this equation, what's our a value? Yes, so this will be a. What's our b? That's b, and then you have this as c. Okay, and now we can plug in the numbers and solve for this. Okay, so then again, you know you're gonna have two values because you have this plus minus sign, so you're gonna have one root as use plus sign, the other solution will be using minus sign. Okay, so now let's plug in the numbers. Okay, so well, x equals 2 times 4, on top you have negative 0.76 plus minus, then you have negative 0.76 squared minus 4 times 0.01. Okay, and now you solve for this. X equals 2.76 plus minus 0.4176 equals to 0.76 plus minus 0.65. Okay, and then you have two solutions. X1 equals to 0.176 or x equals to 0.014. Okay, and then you go, am I gonna get two different sets of concentrations at equilibrium? Probably not. One will be actually make sense in this question, the other one will not. And the one won't make sense will be this one. They wouldn't make sense. Why? Let's go back. Okay, so let's look at our expression. If this x value equals to 0.176, okay, just say if this x equals to 0.176, when you put into this expression, you will have a 0.1 minus 2 times 0.176 you will have a negative value. Okay, so you're gonna have a negative value. Can you ever have a negative concentration? No, you can't. Therefore, this 0.176 wouldn't be one of the solution fit back into this chemistry question. Okay, so therefore our x will equal to 0.014. Now you're gonna plug in back into this expression. So at equilibrium, okay, so at equilibrium we will have that the concentration of N2O4 will equal to x, that will be just 0.014, okay, and the concentration of NO2 will equals to 0.1 minus 2 times 0.014 gives us 0.072. Okay, so this will be the concentrations at equilibrium for our question, and then this is your answer. Okay, so one more time, for this is similar type as the earlier example. Now the same strategy, it just come to this. You have to calculate express k, calculate q, compare q and k, then you'll be able to determine which direction it goes, and then it matters to the signs over here. Okay, and then after that you'll be able to express equilibrium concentration, put it back into the case expression, and then all the way come to here. It's the same strategy. The only difference will be the last question you can use square root. The math will be easy. In this question you have to use a quadratic equation because that wouldn't work. You cannot just use a square root for the calculation. Okay, so that's the difference. And then this is another example. One more time, you know the equilibrium constant, initial concentrations. You're looking for the equilibrium concentrations. Thank you for listening.